Welcome to the Explainer. Today, we're diving straight into the hidden mathematical engine that keeps everything, from drones to heavy industrial robots, perfectly stable. It's a really fascinating problem when you think about it. Physics is just inherently chaotic, right? You've got wind buffering drones, friction grabbing at robotic arms, sudden temperature shifts in chemical plants. So how do we actually achieve absolute, optimized precision in the face of all that chaos? Well, the answer lies in combining three distinct mathematical actions: proportional, integral, and derivative. Think of them as puzzle pieces. But as we're going to see throughout this explainer, the real magic isn't just slapping them together. The secret sauce is how tuning optimizes these systems to achieve a flawless balance of speed, accuracy, and stability. Okay, here's our roadmap for today. We're going to start with the quest for stability, break down the anatomy of a controller, and look at their strengths and fatal flaws. Then, we'll find that Goldilocks zone, learn about tuning for optimal performance, and finally, wrap up with some practical application strategies. Let's get into it. Section 1. The quest for stability. Before we can fix or optimize any system, we need to know what a successful control system actually looks like on paper. So when we give a machine a command, say telling a drone to hover at exactly 10 feet, we judge its performance by a few key baseline metrics. First, we look at the rise time, which is basically how fast it gets up there. Next is the overshoot. Does it wildly blast past 10 feet before coming back down? And finally, we look at settling time and steady state error. Basically, does it eventually settle exactly on the target, or does it hover forever at like 9.8 feet, leaving this permanent gap? All right, moving to Section 2, Anatomy of a Controller. To master those metrics, let's interview our three candidates for the job, starting with plus. Think of proportional control as the brute force muscle of the whole operation. It reacts instantly to the current error. If you're really far away from your target, it pushes hard. If you're close, it pushes gently. It's giving you a response that is directly proportional to your current distance from the goal. Now, the crucial point here is that while PID Control is incredibly fast, simple, and super cheap to implement, kind of like pulling a block attached to a spring, it has a fatal flaw. As the error shrinks and you get closer to the target, that proportional force weakens. Eventually, the pushing force gets so weak that it literally can't overcome basic system friction. It just stops, leaving a persistent gap. In the engineering world, we call this a steady state error. To fix that persistent gap, we bring in I. If P is the muscle, well, I is the memory. Integral control looks backward in time to add up all your past errors. It basically says, hey, we've been sitting 0.2 feet below our target for 5 seconds now. I'm going to build up enough power to push us exactly to the finish line. But notice the trade-off with the accumulated error history. Integral absolutely destroys that persistent offset. The steady state error drops to absolute zero. Boom. But because it acts on the past and builds up over time, it's pretty sluggish to react, and it severely degrades system stability. It ends up causing these wild looping oscillations before the system finally settles down. So we've got the muscle, we've got the memory, and finally we have D, the anticipation. Derivative control looks at the rate of change of the error right now. It calculates your speed to predict exactly where the system is going in the immediate future. The D control acts like a set of highly aggressive brakes. By predicting the future trajectory, it vastly improves stability by dampening the system as it approaches the target. But, and it's a big but, its fatal flaw is that it can't reach the final target on its own. Plus, because it's reacting to the tiniest sudden changes in speed, it is exceptionally sensitive to high-frequency noise. Think of a jittery sensor. D absolutely hates that. Section 3, Strengths and Fatal Flaws. We've seen them all in isolation now, so let's summarize exactly why none of these work perfectly on their own. This matrix perfectly captures the engineering headache. P lacks precision, I lacks stability, and D lacks follow-through. P leaves an error, I makes the system bounce all over the place, and D gets totally confused by sensor noise. This practically demands that we combine them so they can cover each other's blind spots. Which brings us to Section 4, Finding the Goldilocks Zone. Let's see what happens when we actually put these puzzle pieces together. Because just mashing them into one equation isn't the whole story. Honestly, this is the most vital takeaway of our explainer today. Anyone can throw P, I, and D together, but having a PID controller isn't enough to prevent a total disaster. The real secret to how tuning optimizes systems lies in meticulously adjusting the mathematical weight, or gain, of each individual component. Let's look at the visual proof of this optimization. In one scenario, we have a PI controller. Remember, integral eliminates the offset, but it heavily compromises stability, giving you those massive, wild waves. But in the full PID scenario, by tuning in that derivative component, applying those anticipatory brakes, we aggressively dampen those oscillations. The mathematical tuning of these specific gains allows the system to hit the absolute Goldilocks zone of performance: fast, perfectly accurate, and highly stable. Section 5. Tuning for optimal performance. So how exactly do we achieve that perfect tune in practice? Like, which dials do we actually turn? Well, engineers rely on a diagnostic matrix, kind of like a heat map, to understand the trade-offs. For example, look at the integral action. Cranking up your integral gain, or K sub I, will perfectly eliminate your steady-state error. That's awesome. But it simultaneously punishes your system by increasing overshoot and settling time. Fixing one operational metric almost always degrades another. Because of these complex, interconnected trade-offs, engineers rarely do this by hand anymore. I mean, who would? Instead, they use software architecture, like MATLAB, to instantaneously simulate thousands of gain combinations. This lets them systematically identify the exact, mathematically optimized tune without breaking any physical equipment through trial and error. It's a real game changer. Finally, Section 6, Practical Application Strategies. To wrap this explainer up, let's take these tuning theories out of the simulation software and put them into the real world. The reality is, not every system actually needs full PID control. It's a balance of system stability versus accuracy. Sometimes, PI control is the absolute industry standard, like in fluid systems. If you can tolerate a little temporary bounce, but need to ensure a persistent offset is completely gone. On the flip side, PD control is often perfectly reserved for servo motors or robotic arms, where you absolutely must prioritize extreme stability and dampening to avoid crashing, even if it means tolerating a tiny offset error. It's always a game of give and take. Understanding how tuning optimizes systems is exactly what makes modern automation possible. By carefully weighing the muscle, the memory, and the anticipation, engineers can tame the chaos of the physical world. So, the next time you fly a drone or set your thermostat, ask yourself, what were the engineers prioritizing here? Was it tuned for blistering speed or absolute uncompromising precision?